All right, so today we're going to talk about one of the coolest, most powerful ideas in all of machine learning. It's called ensemble learning. And really, it's this idea that a whole team of pretty good models can absolutely crush one single genius model. To really get why this is such a game changer, we've got to rewind the clock back to 2006.
So, back in 2006, Netflix had this massive problem. I mean, their entire business, their whole reason for being, hinged on one thing: keeping you glued to the screen. And to do that, they had to get ridiculously good at predicting the very next movie you were going to fall in love with.
And that's the multi-million-dollar question, right? You've got millions of users, thousands and thousands of movies. How in the world do you build an algorithm that can actually figure out something as personal as taste? Their system at the time, it was okay, but okay wasn't going to cut it. They knew it could be way, way better.
So, what did they do? They threw the problem out to the entire world. They launched this massive public competition, the Netflix Prize, and put a cool $1 million grand prize on the table. The goal? Be the first team to improve their recommendation engine by just 10%. Sounds easy, right? It wasn't. This thing ran for years. It drew in something like 40,000 different teams, all trying to crack this problem. And when a winner finally emerged, their solution was, well, it wasn't what anyone expected. You'd think it would be some single, brilliant, revolutionary new algorithm that just saw the problem in a totally new way. But nope.
The winning team, great name by the way, Belcore's Pragmatic Chaos, they didn't build one supermodel. Instead, what they did was build a system that took the predictions from 107 different models and blended them all together. And by combining all their individual strengths, they got to a place that no single model could ever reach on its own. That is the big idea behind ensemble learning.
Okay, so to really get why this whole team of models approach is so effective, we need to talk about a really fundamental challenge in machine learning. It's called the Bias-Variance Dilemma. And honestly, it's the main reason why trying to build that one single perfect model is just so ridiculously hard.
This trade-off is, well, it's everything. On one side, you've got high bias. This is where your model is just too simple. It's underfitting. Imagine you have a bunch of data points that make a nice curve, and you try to fit them with a straight line. That line is just too stubborn, right? It completely misses the real pattern. Then on the other side, you've got high variance. This is where your model is way too complex. It's overfitting. It's so jumpy and erratic that it tries to perfectly hit every single data point, which means it ends up memorizing all the random noise instead of the actual signal you care about.
And this visual really nails it. Look over on the left. That's the bias problem. That simple line just can't capture the true complex reality of the data. It's just consistently wrong. Now look at the right. That's the variance problem. You see all those squiggly lines? Each one is a model trained on slightly different data, and they're all over the place. None of them are reliable because they're just reacting to noise. So if you look at it mathematically, a model's total error is basically a combination of its bias, its variance, and some noise you can't get rid of. But here's the kicker. They're like two ends of a seesaw. When you push down on bias to make your model more complex, variance usually goes up. And when you try to simplify your model to lower the variance, its bias tends to creep up. It's this constant balancing act. So, how do you win? How do you get the best of both worlds?
Well, this is where the magic of teamwork comes into play. Ensemble learning gives us a super clever way to handle this trade-off. The secret isn't to build one perfect model. It's to combine a bunch of imperfect ones.
So formally, ensemble learning is just a set of techniques where you combine multiple models to get a better result than any of them could give you alone. It's really that simple. It's the wisdom of the crowd principle, but applied to algorithms. Now let's check out the two most popular ways this is done.
First up, we've got a method called bagging. Now that's short for a bit of a mouthful, Bootstrap Aggregating. The easiest way to think about this one is as the diversity of opinion method. Its whole purpose in life is to take those jumpy, high-variance models and calm them down.
And the process is actually pretty straightforward. Here's how it works. Step 1, you take your original dataset and you create a bunch of random little subsets from it. The key here is that you do this with replacement, which just means you might pick the same data point more than once for a single subset. This creates a lot of variety. Step 2, you train a completely separate model on each of those unique subsets, and you do it all at the same time, in parallel. And finally, step 3, you just mash all their predictions together. If you're predicting a number, you average their answers. If you're predicting a category, you let them vote. This diagram lays it all out beautifully. See? You start with your one big data set on the left. Then you bootstrap it, creating all these slightly different mini data sets. Each one of those gets fed to its own model, usually decision tree, and they all train in parallel. Then at the very end, you aggregate all their opinions into one single, much more stable and reliable prediction. It's that final averaging or voting that cancels out all the random noise and jumpiness from the individual models. All right, so our second major technique is called boosting, and it's a totally different philosophy. If bagging is like asking a diverse crowd for their opinion, boosting is like building a team of specialists, one by one, where each new member's job is to fix the mistakes made by the person before them.
So right away, the big difference is that boosting is sequential, not parallel. It works like this. You train a simple model. You see where it messed up. Then you train the next model, but you tell it, hey, pay extra attention to all the spots where the first model got it wrong. It really is like a relay team, where each runner is trying to correct the path. And the goal here isn't to reduce that jumpiness, that variance. The goal is to reduce bias, to take a simple, kind of dumb model and slowly make it much, much smarter.
Okay, check out how this works. You start with your data, and you train tree 1. It makes some predictions, but of course it makes some mistakes, right? The difference between its prediction and the real answer, we call those residuals, or just errors. Now here's the cool part. Tree 2 doesn't get trained on the original data. It gets trained on the errors from tree 1. Its entire job is to predict the mistakes of the first model. Then tree 3 learns from the mistakes of tree 2, and on it goes, with each new model getting better and better at cleaning up the mess left behind.
Let's make this super concrete with some house prices. Say a house is actually worth $480,000. Our first simple model predicts $440,000. Okay, so it's off by plus 40 grand. The next model's job isn't to predict the price, its job is to predict that plus 40K error. And for the next house, maybe the error is plus $210,000. That's what the next model learns. By the time you add up what the first model said, plus the correction from the second, plus the correction from the third, you slowly boost your way to a really accurate answer.
So there you have it. Two really powerful approaches, bagging and boosting. They both use a team of models, but they could not be more different in how they get to that final, smarter result. Let's put them head to head and really break it down. Okay, if you remember just one thing, make it this. If your problem is a model that's too complex and jumpy, in other words, high variance, use bagging to average out all that noise. But if your problem is a model that's too simple and stubborn, high bias, you use boosting to teach it, step by step, the patterns it keeps missing. Let's just hammer this home one last time. Bagging trains models in parallel. Boosting trains them sequentially. In bagging, every model gets an equal vote. In boosting, some models have more influence than others because they're weighted by how well they perform. And the bottom line? Bagging is your weapon for fighting high variance. Boosting is your weapon for fighting high bias. Two different tools for two very different problems.
You know, from that original Netflix prize, all the way to predicting the stock market, or even diagnosing diseases, Ensemble Learning shows up everywhere. It's this powerful reminder that combining different perspectives, whether they're diverse or specialized, almost always leads to a better, stronger result. And that kind of leaves you with a bigger question, doesn't it? If this wisdom of the crowd idea works so incredibly well for algorithms, where else could it help us solve the really big, seemingly impossible problems we're facing?